Again, my name is David Eastwood, Geotech Engineering and Testing. We're going to be talking about pavement evaluation, asphalt road. Interesting project that we worked on. We got about 170 people RSVP'd on this thing. We have a lot of engineers, city engineer, county engineers, civil engineers, transportation engineers that are listening in, developers. This is my contact information. My phone number is 713-699-4000. My email is de@geotecheng.com. This program is going to be on the YouTube, and so you can always go back and watch it. I was looking at the YouTube channel. We have these Geotech Engineering and Testing YouTube. We have about 34 programs. You can go out there, watch what you need, and send us an email. We'll send you a certificate. So you can get that for your continuing education, for your PDH. We're located in Houston. We've been around for 39 years. We do geotechnical, environmental, materials, geoforensic engineering, pavement failure, slope failure, retaining walls, foundations. We have 60 people. We work all over Texas, Louisiana, New Mexico, Oklahoma, New Mexico, and Arizona. And we have on all rigs, we got like 10 rigs, so we can get on projects quickly. If you have questions, I guess you can put it in the chat or Q&A, and I'll respond to it as soon as I get your question. It's kind of a picture of a project. The whole deal was there's this big asphalt road. It's a 2-lane asphalt road, and they were developing all these big subdivisions around it. And the city where this thing is located, they weren't getting any money from the developers and for the maintenance of the road and stuff. And they wanted the developers to chip in. And so the developer got with us and say, well, let's look at this pavement to see if you can handle our traffic loading that we have for the next 10 years. And what's the condition of the existing pavement here? So that was our mission, to look at the condition of the existing pavement and see if he can handle the projected traffic loading that is going to be because of the developments around the road project. The project site picture, basically the agenda is we're going to have some pictures of the site, types of distress that we saw. You can see we're going to go over pavement condition index project that by U.S. Army procedure. We talk about some of our field exploration, laboratory testing, and pavement redesign, reconstruction, or repairs for these pavements. Here's the two-lane asphalt road. Actually, subject to a lot of development going out there. So there's a lot of residential development. So there's some distress in some of these pavements, a lot of cracking and potholes. A lot of edge cracking, and you see a lot of the pavements, asphalt pavements around the Houston area, they have this edge cracking because of presence of the open ditch and trees, and that happens, because both the trees and open ditch, they take a lot of moisture, evaporation, and of course the trees suck the moisture, and as they do that, a distance from the edge of the pavement of about 9 feet, that's the area that usually the open ditch causes problems, and you're going to see these cracks, and they don't go away. And so you can go out there and repave it, but it shows back up again. You can put overlay on it; it will still show up on it. And, so to treat it, you're going to have to do curb and gutter, or go concrete paving, or you can do what's called chemical injection all the way down to a depth of 10 feet. Or remove the expansive soils, replace non-expansive soils. but that still is going to cause problems because of the moisture removal due to the presence of open ditch. Again, more cracks. Again, a lot of edge cracking. So you can see all these different types of distress on the pavement structure. That potholes that had backfilled. So it was not in the best condition, but because of the high traffic loading. Some areas, again, the potholes were repaired. A lot of edge cracking. Basically, some of the distress you see on asphalt pavements, some of them are alligator cracks. It's a series of interconnected cracks that are caused by fatigue failure on the repeated traffic loading. And you can see a medium severity alligator cracking. This is a high severity alligator cracking. Bleeding. Bleeding is basically a firm asphalt material that on the pavement surface, which creates a shiny, glassy, reflecting surface that usually becomes quite sticky. And caused by excessive asphalt cement or tars in the mix of the asphalt. So here's block cracking. Basically, interconnected cracks that divide the pavement into irregular rectangular pieces. This is a kind of a low severity block caused by shrinkage of the asphaltic concrete and daily temperature cycling. Medium severity block cracking. High severity block cracking. Corrugation is basically a series of closely spaced ridges and valleys occurring at a fairly regular intervals, less than 10 feet. See it right here. You see it over here. It's basically caused by traffic action combined with unstable pavement surface or base. We see a lot of depression in the pavements, localized pavement surface with elevations lower than the area around it, called depressions. See the depression here? Here's a big one. Polished aggregate basically what happens is caused by repeated traffic application when the aggregate in the surface becomes smooth to touch. Adhesion between the vehicle tires is considerably reduced. Polished aggregate. Raveling. Raveling is basically when the aggregates are coming off the concrete mix. Basically because of the loss of the binder, asphalt binder. You can see a low severity by traffic. Medium severity and high severity raveling. Okay, here got shoving. It's basically a permanent longitudinal displacement of localized area of pavement space by traffic loading. This is the shoving here, right there. When the traffic pushes against the pavement, it produces a short, abrupt wave of pavement surface. It's called shoving. Shoving normally occurs on unstable liquid asphalt pavements. Pavement condition survey. So one of the things we did on this project, we went out there and do a pavement condition survey developed by U.S. Army Technical Manual 5-623. Okay, it's a manual that goes through the procedure. Essentially, you look at all the cracks and depressions and pavement distress, and based on that, you're going to rate that pavement. And so, if your number is 0 to 10, your pavement has failed. Between 10 and 25 is very poor. Between 25 and 40 is poor. Between 40 and 55 is fair. Between 55 and 70 is good. 70 to 85, very good. And above 85 is excellent. They call it pavement condition index. I see it all over the place. Basically, you look at the pavement structure on the road. You divide it into sections. In this case, we broke that pavement into 7 sections, and we evaluated the PCI pavement condition index at each of the 7 sections that we did. Basically, when you go through it, you got to go. There's a form that U.S. Army has that you go through it, and based on the stress type, you go through it. For example, in this case, is an example of a section that we've had on this project, about 1,000 feet long and 32 feet wide, about 32,000 square feet. So here is 3 type of the distress block cracking that we have. We had in this 1,000 feet an 8 foot by 17 foot of low intensity severity block cracking. Then here is the top 8 joint reflection cracking. Here we had 1,000 feet, 1,000 feet, 1,000 feet in this area of mediums severity reflection cracking, joint reflection cracking. Here in this column, we have type 1 alligator cracking. In this 1,000 feet by 32, we had 4 by 43, 6 by 40, 6 by 33, and 4 by 13 low severity alligator cracking. Come over here, 7 edge cracking, an area 70 feet and 300 feet. Basically, we had edge cracking. One of them was a medium severity. The 300 foot long was high severity. 10 longitudinal and transverse cracking. We have one area 40 feet long, medium, another 70 foot long, medium. You add it together, it's 110 feet total. Okay, here is about 3,000 square feet here. Here's 136 square feet. So usually as a square feet, for example, you get what's called density. To get the density, you take the area and divide it by 32,000. This is the 1,000 feet by 32. So you got 3,000 by 32. So the stress number 1, for example, that's number 1, is 662 square feet. You take 662 divided by 32,000. You get 2.07. It's called density of low severity of type 1 distress, which is alligator cracking. Here's number 3. We got 136 over 32,000. 0.43 low severity. Low severity. That's a density 0.43. Next one is 7. You got 370 essentially total. The density on that is 0.22. of medium size. And again, 7.94 of a high kind. The high is 300 square foot, 300 foot. So basically, you go through the density on these things. You get the density, and once you get the density at each one of these things, you go through what's called a deduct value. And what that is you go through the density, you go through these curves in here, depending on low severity, medium severity, and high severity. This is for longitudinal and transverse cracking. This is low density, you get a deduct value. Again, for alligator cracking, you get the density. You go to these curves, it's a medium severity. You get a deduct value. And here's the actual basically graph that developed by with the U.S. Army. Let's say your density is 5, and you got a medium severity distress of alligator cracking. Your deductive value is 40. Okay, so going back here, if you got 2.07 density here for type 1, which is alligator cracking, you go to alligator cracking at 2. So that's medium. That was low, I think. Let me go back again. I forgot what it was. Okay, it was low. So 2 low, you get a deduct value of here, roughly about 15 or so. So it's 16, okay? So you get a deduct value of 16. You do the same thing for all the other kinds, okay? You got all these different densities for different types. Number 3 is 0.43. So that's number 3, which is block cracking. Density is 0.43. So you go block cracking 0.43. It's right here. I think it was medium. It was almost 0. So going back, number 3 is 0. So the deduct value is 0. You go to distress type number 7, edge cracking. Okay. One of them was medium 0.22. So you go to edge cracking 0.22, and that was medium. You should get somewhere about 5 or so for medium. So you going back here for medium, you get 4. So anyway, you go through each one of these distress value areas, and you add them all up, and you total deduct value of 67. And so after you get that, there's what's called a corrected deduct value, CDV. Okay, so you got to make a correction on these things. And the way you do it is, you do, after you go through these charts, you look at total deduct value, and here's the number of the entries with deduct values of over 5 points. And then here you get the corrected deduct value. Okay, he said this is the actual chart in here. So if you go back again, in here, our total deduct value was 67. And the things that were higher than 5 was 1, 2, 3. 3 of the deduct values were greater than 5. So you got only 3 of them. 67 and 3 values greater than 5. So if you go there, 67 and 3, Q is 3. The Q is the number of deducts greater than 5 points. So you go over here, you get roughly 45. Corrected deduct value. Okay, so that's the correct 45. Actually, it's 42. So we got. So that's corrected value of 42. You subtract that from 100, you get a 58. That's your pavement condition index, which is considered good. So for this 1,000 feet by 32 feet, overall rating value indicates the pavement is in good condition. Okay. So we basically took that pavement and then put it in 7 segments. Here's another 1,000 feet by 22 feet. Went through all the cracking and stuff like that, density, and we got a corrected deduct value of 51. We subtract that from 100, you get 49. That means that this segment has got a rating of fair. The next one is 31 feet by 1,000 feet segment. We got a PCI of 56, which means this section has got a rating of good. Here's another one here is a segment 34 feet by 1,000 feet. Your PCI is 55. That means fair. Here's another segment 5,000 feet by 34 feet. And we got a PCI of 48. That was fair quality. Here's another one 28 foot wide by 500 foot long. We got a rating of 68. That means the pavement is in good condition. And then last segment, 24 foot by 290 foot long. Rating was 80. It's a very good condition, that pavement. So use the pavement, basically the pavement rating system that we got that range between 48 and 50. So our pavement, basically performed from fair to very good. But that's for the existing condition of the pavements. It doesn't account for the future traffic loading. So your PCI may be good, but if your pavement traffic load is going to increase with time, the PCI doesn't work. This is in summary. The segment 1, we had a bunch of alligator cracking, block cracking, edge cracking. Our rate was 58, was good. Segment 2, we had alligator cracking, edge cracking, joint reflective cracking, and longitudinal and transverse cracking was fair. Segment 3 was 56. That was good. Segment 4 was 55. That's good. Segment 5 was 48, which is good. Segment 6 was 68. That's good. Segment 80 had less alligator cracking, edge cracking, and longitudinal trans cracking, and then the PCI was 80. So that was a very good condition. So what we did is we went out there and did some field exploration to see what pavement structure looks like. We did pavement coring and drilling and sampling. That's the project alignment. We did borings along the project alignment. So looking at it, I think we did like 17 borings. First, we had to core the existing pavements. So we had a coring machine here. We core the actual pavement and the base. This is the asphalt pavement, and here's the base. Like you can see, it's a crushed limestone. Here's another coring here. Here's coring here. Again, we're coring in here. We see the asphalt pavement and the base, crushed limestone. Again, you look at the cores in here, you got asphalt pavement, base, and stabilized subgrade. We cored the stabilized subgrade as well. So you can see the asphalt, the base course, the stabilized subgrade. Notice this is kind of pink. This is because we put what's called a phenol failing on it to see if there was any lime or cement in it. If it did, it will turn pink. Okay. Again, pavement, asphalt, the base, stabilized subgrade, asphalt, the base, stabilized subgrade. It's a little pink. That means there's some lime or cement in it. Asphalt, base, stabilized subgrade. These are the holes that shows the asphalt. Here's the base. Here's the asphalt. Here's the base underneath in the hole coring. Asphalt, here's the base. And after that, when we cored it, we went out there, drilled, and tried to get some soil sample underneath it. So we used our drill rig and did boring out there to get some samples of the soils. Got soils extruded. We found a lot of fat clays there. We measured the water level to see if there's any water there. When we finish the borings, we grout the holes. We fill them up with cement and grout, cement and bentonite to fill up the hole. Just kind of mix the whole thing together in the bucket and just push it under pressure from bottom up. Fill up the hole. We probed it, make sure that the plug was the whole, the hole was grouted properly, so that there's not going to generate a hole there, or somebody step in it, or so it was grouted. Funnel failing testing. If your stabilized layer has cement or lime in it, you can put these chemicals on it, and it will turn purple. It's called funnel failing. So when we core this stuff, we look at the asphalt, the base, and this is the stabilized layer. Here is no funnel failing because it didn't turn purple. Here, the base stabilized layer turned purple. There's funnel failing in it. Okay. Again, you can see in here, asphalt, base, stabilized. Verify that there was some lime stabilized subgrade or cement stabilized. In this case, since the soils were fat clays, we assumed this thing to be lime stabilized. And you can see here the asphalt, the base, this is a stabilized layer. It's got a little bit of purple in it. Here's another one. Yeah, here's another one. You can see the asphalt base, stabilized subgrade with purple. Asphalt stabilized, purple stabilized layer. It had lime in it. Here's another one. Asphalt, crushed limestone base, stabilized subgrade turned purple. There's another one here. Asphalt, stabilized base, stabilized layer. So on, asphalt base, stabilized layer turned purple. This is the last one. Asphalt base, crushed limestone, stabilized layer turned purple. Basically asphalt stabilized base there. Asphalt stabilized base. So when we summarize all this, we had 17 borings. Some of them had stabilized layer. Like this one didn't have. B7, we had no stabilized. And there was actually no stabilized area at B7. Okay. B10 had no stabilization. B12 had 0. B13 had 0 stabilization. And some of them had like 2 inches of stabilized, subgrade. Some of them had 10 inches. So some of them 14 inches. Some of them had no stabilization. We did lab testing, classification tests, string test, funnel failing tests. You plot the borings, B1, you got the asphalt. Below that, you got crushed limestone. Below that, you got stabilized layer. Below that, you got fat clay. B2, you had asphalt, stabilized crushed limestone, stabilized layer. You can see that stabilized layer here is going to vary all over the place. Same as with the crushed limestone base. These are B1 through B9. This is B10 through B17. And you can see in here, this B10, for example, has no stabilized layer. B11's got only maybe a couple of inches. B13 has got no stabilized layer. B12 has no stabilized layer. B15 has got the some. B16 has got some. In general, we had 0 to about 0.25 feet of asphalt paving, 0 to 3 inches in thickness. Below that, you got crushed limestone, 0 to about 13, 14 inches. Stabilized layer, 0 to about 14 inches. Below that was all fat clay. The soil had PIs of between 44 to 72, which was indicating that the soil was highly expansive. Here are the boring logs for the project, like boring B1. We had asphalt paving, about 3 inches, crushed limestone base, and then a stabilized layer about 10 inches. Below that, it had a fat clay with a PI of 40. B2, 3 inches of asphalt, 11 inches of crushed limestone. Stabilized layer was 14 inches. Fat clay underneath it with PI of 64. B3, stabilized layer, asphalt of 3 inches, crushed limestone 12.5, stabilized 6 inches, clay. That was lime stabilized, and below that, fat clay, PI of 69. Going through this here, B7 had 2 inches of asphalt, 11 inches of base, and no stabilized layer, PI of 53. So that's kind of shows the boring logs. Each one of them is kind of different that I went through already. Pavement design. So when we look at this pavement, the PCI, pavement condition index, was fair to very good. We want to know what the pavement structure was. We did the borings and found out the pavement structure was variable. So one of the things we looked at, of course, is the future traffic loading. And based on that, we determine the type of repair, either reconstruction with new asphalt pavement, milling the existing surface and putting a new asphalt layer on top of it, or do full depth reclamation. Basically, the current pavement structure is called minor arterial, and we looked at the AASHTO pavement design and come up with for the next 10 years a traffic loading of 2.4 million ESAL, equivalent single axle loads. That's what you get that from the AASHTO pavement design. So this is our traffic loading, 2.4 million ESAL for the next 10 years. We want to know how this pavement performs under that traffic loading. Of course, the soils underneath the pavement was fat clays. Looking at the AASHTO pavement design, it had a residual modulus of 3. 5,000 PSI was the resilient modulus. CBR was 3. So resilient modulus is usually about 1,500 times CBR. That's California bearing ratio. We ran a bunch of tests on this thing to see what kind of a pavement structure we have. Went through the pavement design by AASHTO. Here's some of the design parameters we used. Traffic loading, 2.4 million. Reliability, 95%. Overall standard deviation, 0.35. Drainage coefficient, 1.25. Design serviceability loss, 2.2. CBR, 3. Resilient modulus, 5. Structural coefficients, basically. Structural numbers are here for asphalt, 0.44. Crushed limestone, 0.14. Black base is 0.34, and lime stabilized is about 0.11. Going through the pavement design by AASHTO, reliability of 95, overall standard deviation. In here, you got the transfer line here. From that, you go to the traffic loading of 2.4 million. Then from that, you go to the effective roadbed soil resilient modulus of 5,000. That brings you right here. And from that, you go to the design serviceability loss of 2.2 right here for this curve. That brings you down to design structural number. In this case, our design structural number was 4.2. So for design structural number of 4.2, We go to Astro Pavement Design. Your structural number is 4.2, A1D1, A2D2, A3D3. This is corresponds to structural number for the material that we're using times the depth. Structural number of the base. This is the asphalt surface, which is 0.44 times the depth. This is the structural number for the base times the thickness of the base. Structural number for the stabilized subgrade times the thickness. A1, A2, A3 are layer coefficients. Basically, D1, D2, D3 is actual thickness. The structural numbers for various materials used for concrete paving, the structural number is 0.5, which is the highest. For hot mix asphalt is 0.44. Black base 0.34. Stabilized, cement stabilized limestone base 0.23. In this case, we have crushed stone. Well, we didn't, I don't know, I'm not sure if it was cement stabilized, but it was for recycled concrete is 0.14. For lime stabilized subgrade is 0.11. So we go through this equation and come up with a proposed pavement design. One option is for 2.4 million traffic loading, you put 3 inches of asphalt on the top, 8 inches of crushed limestone base, and stabilization is the subgrade is 18 inches. Or you can reduce the stabilization by 2 inches of asphalt, 8 inches of black base, and 8 inches of stabilized subgrade. These are a couple of options. You can have a combination as long as your structural number is 4.2. All the cohesive soils on the subgrade, of course, got to be compacted with 9% lime in this case. So going through the segments that we have, segments 1 through 7, our PCI numbers was 58 here. And then in the boring B1, if you go through the structural number for B1 was 3.82, 4.4, 3.08. So in this case, this one does not need the 4.2 design structural number, so you got to do reconstruction or full depth reclamation. But this one is 4.24, and the only thing you got to do here is really mill and overlay. You can do reconstruction, but you don't have to. Segment 2, the structural numbers are all below 4.2, which means that you got to do reconstruction or full depth reclamation. Segment 3, we have 3.7, 3.59, 3.01, 3.4. Structural numbers less than 4.2. So here you got to do reconstruction or full depth reclamation. Here's number 4. You see number 2.4, 3.7. All these are reconstruction or full depth reclamation all the way down for all the sections. So although the pavement was good currently, but if you increase the traffic loading because of the construction of these subdivisions, your traffic loading is going to increase, which means that during this next 10 years, this pavement is not going to be sufficient to be able to carry the traffic loading. So we basically divided the pavement structure along the alignment to 7 segments. This segment is for 1,600 feet. You got FDR reconstruction. This segment 2, FDR, that's full depth reclamation or reconstruction. Segment 3, FDR reconstruction, all the way to this section 7. This section you can do mill and overlay because it was in good condition, or do reconstruction. Full depth reclamation. We really like full depth reclamation. Projects like this, you got asphalt paving. It's a method basically for asphalt paving and reconstruction. Uses the existing asphalt in the base and the subgrade, if it's stabilized, to produce a new stabilized base, and you put an overlay on top of that. It's basically advantages. You can use the on-site material and you don't have to haul in a bunch of new stuff. Not much material's got to be hauled in. You got to put a new asphalt surface course on top of it. Maintain improves an existing grade, conserves virgin material that's already in place, save costs by using in place investment, saves energy, and very sustainable process. The kind of stabilization you can use once you mix the material, you can use emulsified asphalt or foamed asphalt, or you can use a cement. In this case, we recommended using cement. These are some of the pavements that may require full depth reclamation, or if your traffic loading is going to be high and the existing pavement cannot handle it, you got to use full depth reclamation. The application, basically 83% of the pavements in the US are asphalt. 5.7% is concrete. 10.6 is combination of asphalt and concrete. FDR involves mixing up the existing asphalt aggregates, subbase, and underlying soils with chemicals, in this case cement, usually like 7% cement. It goes in there and chops the existing pavements, mix it into small pieces, and then you mix that with cement, and that becomes your base. Typically, again, it says chemicals consist of cement, quick lime. I don't think lime works real well. Basically, you use full depth reclamation if the pavement is seriously damaged. Pavement distress indicates that the problem likely exists in the base or subgrade. Distress will require full depth patching over 20% of the area, or pavement structure is deemed inadequate for the current or future traffic. So that's our case here, that the pavement structure is not adequate for the future traffic. These are some of the pictures that shows which type of pavements use full depth reclamation. Benefits, of course, increase rigidity of the spreads the loads, eliminates rotting, reduces more susceptibility, reduce fatigue cracking, allows thinner pavement sections. The way you design it is you look at your pavement design procedure. You can use mechanistic design, empirical design, or mechanistic empirical. There's a pavementdesigner.org is a software you can go to and design the pavement. In this case, we use the empirical Ashton 1993 pavement design. In terms of the materials, we got to do sieve analysis, make sure it's got proper gradation, Heidelberg limits, moisture density, and compressive strength. In parts of the state where you have high sulfate, you got to check for sulfate. I was talking to the Galveston County guys the other day. They have calcium sulfate as base and under some of their roadways. So if you do full depth reclamation in Galveston County, where you got full depth reclamation, you cannot stabilize that subgrade because you're going to get sulfate heave. Sulfate mixes with the soil, with lime, if you lime it, and it starts heaving and destroys your paving. So you got to be very careful if you're doing project where you got stuff that's got sulfate in it as a base, like calcium sulfate that's under some of the Galveston County road projects. Make sure after you pulverize this stuff, 100% passes number 3 inch, minimum 95% passes number 2 inch, 55% should pass number 4 sieve for the gradation of the pulverized material. This is your Proctor curve. You get them all mixed up and you compact them. You get a maximum dry density of 120 up to a moisture of about 10. Also, the mixed material with cement should have a 7-day strength of about 300 to 600 psi. Majority of the state like TxDOT and all that use some kind of a strength values with the project requirements, proven strength and performance in both and wet and freeze thaw environments. Construction, this is your existing paving. You got a beat up asphalt pavement, surface course. You got your base. You got subgrade that's stabilized. You go out there and pulverize these three items. That's the area you're going to get. That's the volume. Well, you're going to go haul off some of it off near the surface to allow for put a surface course on top of it. Let's say 3 inches of asphalt. So you have to scrape off the top 3 inches. Then you pulverize what's called material with cement, and you stabilize it. This is your subgrade. This is your stabilized area. And then you put a new asphalt surface course on top of it. This is going to be your final construction. That's the machine that pulverizes the asphalt. It's got these little blades underneath it that chops up the asphalt. And it's going that way. That's what it looks like. It pulverizes to the appropriate gradation. Usually 1 pass or more is required. They can go up to about 24 inches deep. You remove the excess material, shape the reclaimed material to meet the design. Make sure you got all the elevations. Then you bring the cement in it and mix with it, usually about 7%. You mix it, average of 7% cement by dry weight. Blend it in and compact it right away. Water is added, brought it to the optimal moisture. Got to compact 95 to 98% of proctor density. Then if you let it sit there, let it cure for a little while, either add water to it to let it cure, or you put a tack coat. Here's the stabilized layer. If you can go look at it. After it's stabilized, this is the existing asphalt and the base and subgrade mixed. That's what it looks like. That's the stabilized layer. It's the asphalt on top of it. Basically, the testing that you will do is you make sure you got proper gradation, as we talked about. 100% pass number 3-inch sieve, 95% number 2 sieve, 2-inch sieve, and 55% should pass number 4 sieve. We check for moisture is within 2% of the optimum, and then you run density 98%, ASTM D558. Then you turn it to traffic. You can complete it and turn it to traffic immediately and put asphalt course on top of it, of course, later, or you can do it right away. You put a tack coat, and then you put asphalt surface course on top of it. The cost a couple years ago ran about $9 to $13 per square yard for mixing, compaction, and finishing. Basically, the way you do it in terms of after you stabilize that subgrade for full depth reclamation, you go in there and you put a tack coat in, you bring in your asphalt, and lay it on there. You compact it. In terms of another repair, of course, with mill and overlay, if you have a good condition pavements, you got to go out there and basically mill the existing asphalt paving with a milling machine. You take out all the asphalt. This is after milling. You go out there and put a tack coat on it. That basically is a tack coat. Is a binder that attaches the base to your asphalt paving. It's a bonding agent. It's an asphalt emulsion, MC30 or MC70. Bring in your asphalt. Start laying it on there. And then compact it with steel drum roller. That's what it looks like. Run density tests. Make sure all the densities pass. Usually run 3 densities per every 100 foot to verify rolling pattern. You core it every 300 to 500 feet. Make sure you got proper thickness of asphalt. We find out we don't have enough asphalt thickness in a lot of projects, so make sure you core it. And you run these tests in the lab. Maximum theoretical density, super pave, gradation, asphalt content. So that's it. Program evaluation. I want to know how y'all like this program here today. Do you learn anything? It's an interesting project. We're launching a poll. Tell us what you think. This program is going to be on YouTube. And you can go watch it again and send us an email. We'll send you a certificate. Here's my contact information. de@geotecheng.com, 713-699-4000. We're going to have several upcoming webinars that you're going to get notices of. You're going to get your PD Edge within a week for 1 hour watching this program. Questions? Everybody's so shy. Any questions? Let's see what we got here. Can you share a PDF? The presentation is going to be on YouTube. Can you add a lane when you do an FTR? I guess if you have enough material, you can do that. Sometimes you may not have enough material to do add a lane and do FTR. So let's see, you got any other question? No questions. Is it going to be titled the same on YouTube? Yes, it is. How many dogs and cats you have? I have 6 cats and 3 dogs and 23 chickens. Thank you. Are there any cases where you would want to use full depth reclamation instead of full depth replacement? Usually full depth reclamation is cheaper. That's why we would use it. Again, you don't have to take as much material out and stuff like that.